Now then there is another effect that we haven't talked in previous lectures about, that is, in these barriers, that the effective mass is actually slightly different than the effective mass in the conduction band edge. The effective mass in these barriers is different than the effective mass in the wells. That means the transverse momentum in these devices is not perfectly conserved. So you really ought to treat every angle of injection of carrier slightly differently. That is sort of similar as having, in the optics realm, a dielectric constant that is frequency dependent. In that sense, you can look at a RTD as a layered structure where for different angles the propagation constants are going to be slightly different because the momentum is not exactly the same for the different materials because the effective masses have changed. You can kind of see that in the equivalence of the wave equations here where you see on the bottom the wave equations, on the left the Helmholtz equation for the electric field, and on the bottom the Schrödinger equation. And you can sort of see the equivalence that the momentum in the optical realm is proportional to the dielectric constants, and same the momentum in the Schrödinger equation is proportional to the effective mass. So if the effective masses vary as a function of material and frequency, it's similar to having the dielectric constants vary in the optical realm. And if you do that, it modifies basically the peak a little bit, but not a whole lot in an effective mass model. It is, however, of incredible importance in a full band model, and we'll talk about that in a little while later. So now here's the proof that's in the pudding, right? The concept was that a carrier can come in, as sketched on the bottom left, at a high energy, scatter down, and come out, right? That is the idea of scattering, of why valley current might increase by scattering, because there's no more coherent path to go through. All right, so shown in green is an experimental curve of a device, and in black on the right is a calculation that on the peak overlaps reasonably well on the log scale, but the valley current is underestimated by 3 orders of magnitude. 3 orders of magnitude too small. This is at a low temperature RTD. If you put in polar optical phonons and interface roughness scattering into NEMO, you can overlap experiment and theory. Now you say, well, this is on a log scale. Let me see this a little bit more closely. Now it's on a linear scale, zoomed in. In the experiment, we designed a device that will have a phonon echo that is nicely visible. And indeed, you see the phonon echo in the experimental data. And you can get reasonably close with a NEMO1D calculation in terms of absolute scale. Okay? So scattering raises the valley current by several orders of magnitude in these low temperatures RTDs. Indeed, scattering in the central RTD is important at low temperatures. The problem is that while you might get very good agreement in these devices that are just shown at 4.2 Kelvin, and you can get this valley current right, you can't really do that for high temperature devices. Now here is the same device measured at different temperatures. And what you see is there's this nice valley current that looks all pretty. You set the temperature to 77 Kelvin and the phonon peak sort of vanishes, or is not very strongly visible, and the black line, the turn-on the device moves to lower voltages. And if you move this to 300 Kelvin, the turn-on has moved dramatically over to lower voltages. So instead of turning on at 4 Kelvin, your device turns on at roughly 0.75. Then at 77, it turns on at 6, 7, 8, no, somewhere at 0.6 or so. And then at room temperature, it turns up roughly at 0.4 volts. So the turn-on of the device changes dramatically with temperature. Okay? So the scattering does not explain. You can do whatever you want in terms of increasing scattering strength inside the RTD. It will not give you this turn on. So again, at room temperature, if I go back to the original device I had shown, the gas device, we can turn on scattering at room temperature again, and all we're going to do is lower the peak current a little bit, because scattering does lower the peak current, and we increase the valley current by a little bit, and we're still not getting the turn on right. Okay, so we're throwing the whole guns, I mean the big cannons at this problem, the biggest thing we can do, and we're still not doing things right. So we're missing something. We're doing this with different approximations to phonons. We're still missing something. If you do the same calculation without scattering in a 2-band or a 10-band model, you're already getting closer. That's sort of the introduction to the next segment, where we're going to show that getting the turn on right is strongly dependent on doing the band structure right. Okay? Any questions? Yesterday you had some questions on scattering and all that. Does that clarify it a little bit? No questions? I must be crystal clear. Don't worry, there will be 5 questions on the exam on that.